graphical representation of isothermal process of expansion and compression. First, single stage process. Single stage process. Say that isothermal expansion or compression we are trying to represent graphically. Now first we are selecting that single stage expansion or compression. This is expansion, this is compression. See, during the expansion, say first let us say we have taken the gas up to this level. This is the movable piston. This is the movable piston. See, for expansion to take place, we have to lift the piston. So here in the isothermal reversible process that is taking place in a single stage, in a single step suddenly we have removed the piston from this level to this level, let us say. Initially if the pressure of the gas is 10 atmospheres, if volume of the gas is 1 liter, in a single step if we lift the piston, if the gas undergoes expansion to 10 liters, the pressure will become 1 atmosphere, because at constant temperature P1 V1 is equal to P2 V2. You see here, this is a P1 V1, this is P2 V2, 1 into 10, here 1 into 10. P1 V1 is equal to P2 V2. So in a single step process, we are decreasing the pressure over the gas, means we are lifting the piston in a single step. That means in the experiment we will lift the piston in a single step in this way. The same process now we want to represent graphically. Here on y axis we are taking the pressure, here volume. See, that means initially the gas is having the volume 1 liter. At 1 liter the pressure is 10 atmospheres. That means initially the pressure of the gas is very very high. That initial pressure, let us say, will represent as P1. Now when the gas is at pressure P1, it is having a volume very very less. Let us say its volume is V1. Let us assume this is 1 liter. Let us say P1 is equal to 10 atmospheres. Now in a single step we want to decrease the pressure. In the experiment we will lift the piston in the upward direction, but graphically that same movement of the piston in the upward direction we have to represent graphically. That while we try to represent graphically, the movement will take place in the downward direction. That means initially the pressure is P1. Now if you decrease the pressure to, let us say, 1 atmosphere, that is final pressure is 1 atmosphere. That means here we are just moving in the downward direction. If we move in this downward direction, the gas will undergo expansion in this direction. V2 is equal to 10 liters. Next, whenever at constant temperature if pressure and volume changes will takes place, those pressure and volume changes will always follow the what is called Boyle's law. So therefore we should get a curve like this. But here in a single step, when we suddenly decrease the pressure from here to here, immediately the pressure is decreased, the gas will undergo in this way. That means here, from here to here we are decreasing. Therefore the gas will undergo expansion to this position. That means this is the total expansion shown by the gas in a single step process. This is. Next, see, mathematically we can calculate the work done by the gas by using that formula. Now graphically, how to calculate the work done by the gas? Graphically, if you want to calculate the work done by the gas, you just calculate the total area of this shaded portion. The total area of the shaded portion represents the work done by the gas during expansion in a single stage process. After expansion to this position, again we want to bring the gas back to same position. That change we want to represent graphically like this. Now see, this is the standard pattern of distribution of pressure and volume. Now the gas is here, that means V2 is equal to 10 liters. Now V1 is equal to 1 liter. This is P1, 10 atmospheres. P2, this is 1 atmosphere. Now initially the gas is at this position. When the gas is having 10 liters means the corresponding pressure is 1 atmosphere. Now we want to just compress this gas from this position to this position. In order to compress this gas, we have to just lift the piston. See, this originally the gas is here. Now we want to compress this gas. In order to compress this gas, we have to compress the piston. Therefore, here that means in order to compress the gas, we have to increase the pressure to 10 atmospheres. Therefore, we are increasing the pressure to 10 atmospheres. After increasing the pressure to 10 atmospheres, then this will become the total shaded portion. That means here, first gas is here. The pressure is 1 atmosphere. Now lift the piston to 10 atmospheres. Lift the piston to 10 atmospheres. Now just means straight you write the vertical line. Then connected to the y-axis. Now this total shaded area portion. This total shaded area portion represent the work done by the surroundings during the compression. This one. Now you compare the total area of this shaded portion and area of this shaded portion. Now since the area of this shaded portion is more, therefore we can say the magnitude of the work done by the surroundings during compression is much larger than the work done by the system during expansion. Single stage process. Next, two stage process. Two stage process. This is expansion. This is compression. So this is the initial pressure, 10 atmospheres. When the pressure over the gas is 10 atmospheres, volume of the gas is let us say 1 liter. Now in the previous case, in a single step we have brought the pressure from 10 atmospheres to 1 atmosphere. That means in a single step we have decreased the pressure. Therefore gas has undergone expansion to 10 liters in a single step. That is V2. But now here what actually we are doing is this total expansion process we are conducting in 2 stages. In the first step, we are decreasing the pressure from 10 atmospheres to 5 atmospheres. When the pressure is decreased to 5, that means from here to here we are decreasing. When we decrease the pressure from here to here, the gas will proportionately undergo expansion from here to here. Therefore, this is the expansion done by the gas in this stage. Next, now after bringing the piston to this position, from here onwards again we want to decrease the pressure to 1 atmosphere. 1 atmosphere. When the piston is brought here, now the gas undergo expansion from here to here. Therefore, this is the work done by the gas in the second stage. In the first step, this is the work done by the gas. In the second step, this is the work done by the gas. Therefore, the total work done by the gas in the 2 stages is this one and this one. Now, you compare the total area of the shaded portion, what we got in the earlier process and here. Now, the total area of the shaded portion is more than this much volume. This much volume. That means, if the gas undergoes expansion between similar limits in 2 stages, then naturally the gas will do more work when compared to it will do in a single step. Next, compression. Here this is compression, here pressure and volume. Here pressure 10 atmospheres, here pressure is equal to 1 atmosphere. V1 1 liter, here V2 10 liters. Now the gas has undergone expansion to 10 liters in 2 stages. After expansion to 10 liters, again we want to bring that gas back to its original position. Now in this experiment, we are bringing the gas to original position again in 2 stages, just like in expansion. Therefore, initially the gas is having the volume 10 liters. At that condition, the pressure is 1 atmosphere. Now increase the pressure from 1 atmosphere to 5 atmospheres. So let us say this is 5 atmospheres. 5 atmospheres. Increase the pressure from here to here. Here to here. Therefore, you draw one vertical line parallel to that this one. PV. Now the gas came to this position. When the gas undergo, when the piston is the pressure is decreased to this position, then pressure is decreased. The gas will undergo what is called, see, we are increasing the pressure from 1 atmosphere to 5 atmospheres. Proportionately, the volume of the gas will decrease to this level. So let us say this is a V dash. I will call it as a 2 liters. 2 liters. Therefore, this is the work done by the gas. Sorry, this is the work done by the surroundings during compression. Next, after bringing the piston to this position, now we want to decrease this. Sorry, we want to increase the pressure again to 10 atmospheres. So this is 10. Sorry, 10. Now after bringing here, then again increase the piston to this position. So in the second stage, when the pressure is decreased from 5 atmospheres to 10 atmospheres, now the gas will undergo expansion from this position to this position. This is the total shaded area in the second stage. Therefore, the total work done by the surroundings during the compression is this one. That means when compared to the previous case, see, in the previous case we got the total shaded area portion of this much. Now this is the non-shaded area portion. Therefore, this is the shaded area portion. So the shaded area portion represents the work done by the surroundings. Now the total area of the shaded portion is lesser when compared to the previous case. That means now in the second case, the surroundings are doing lesser work when compared to the earlier work equivalent to this much area. Next, multi-step process. Multi-step process. First, expansion. Next, compression. Compression. So in a multi-step process, so first let us say the pressure over the gas is 10 atmospheres. At that condition, the volume of the gas is 1 liter. Now in a multi-step process, in each stage we are decreasing the pressure to a infinitesimally smaller extent. That means initially the pressure is 10 atmospheres. Now let us decrease the pressure to some 9.9 atmospheres. So that means if this is 10 atmospheres, if we decrease the pressure to 9.9 on y-axis, that 9.9 can be taken as this point. Therefore, when we decrease the pressure by a smaller extent, the degree of expansion shown by the gas is also very, very small. That means in the first stage, this is the degree of expansion shown by the gas. After decreasing the pressure from 10 to 9.9, again from 9.9, again decrease the pressure to another some 9.8. Therefore, again if we decrease the pressure by infinitesimally smaller extent, the degree of expansion will be infinitesimally larger. Here again like this. Therefore, in each step, if the degree of expansion, if the decrease of pressure is very, very small, the increase of volume is also very, very small. Therefore, in a totally infinite number of stages, if the gas undergoes expansion, if we represent the shaded area portion for each stage, we will get the curve like this. you will get the curve like this. Therefore, this is the total shaded area portion that we get during the expansion of the gas in a multi-step which involves the infinite number of stages. Infinite number of stages here. This is the total area. Next, when compared to the single step process and the two step process, now the total area of the shaded portion is much greater. Therefore, we can say the gas can do more work if it undergoes expansion in a infinite number of stages. Next, compression. If the gas undergoes compression in infinite number of stages, now after expansion the gas came to this position. Now we are gradually increasing the pressure. In the first step, we have increased the pressure by infinitesimally smaller level. Again increase the pressure by this much. Again increase the pressure by this much. Again increase the pressure by this much. Like that, in infinite number of stages, if you increase the pressure in smaller portions, therefore we will get the shaded area portions like this. If we join all these shaded area portion, this is the total volume of the work done by the surroundings. Now, if we compare the area of the shaded portion in this graph as well as in this graph, the shaded area portion here and the shaded area portion here are exactly identical. Therefore, the work done by the surroundings during compression is always equal to work done by the system during expansion. Hence, magnitude wise both are exactly identical, but sign is different. This is negative and this is positive. Therefore, total work becomes 0. Expansion into vacuum. This expansion into vacuum is also called as the isothermal adiabatic process, or it is also called as the free expansion. It is also called as free expansion. Here in the calculation of work, according to thermodynamics definition, this is the formula P external dV. Now, if the gas undergoes expansion into the vacuum, the magnitude of the opposing force is 0. Here since P external is 0, therefore work involved is minus 0 into dV. That means it becomes 0. So, by definition, if the gas undergoes expansion into the vacuum, the work done by the gas becomes 0. Here, why the work done by the gas has become 0? Because the magnitude of the external force is becoming 0. That's why work involved in this process is 0. Next, if the work involved in the process is 0, then what are the corresponding thermodynamic changes that are involved here? See here. See, the gas is work done by the gas is 0 means energy spent by the gas is 0. Therefore, internal energy of the gas will remain same. That means change in internal energy is 0. Next, if the internal energy is 0, enthalpy change also becomes 0. Enthalpy change also becomes 0. So, therefore, these are the thermodynamic changes that are taking place in the expansion. Free energy change in isothermal expansion. Isothermal expansion. See, under isothermal expansion process, gas is continuously absorbing the energy. As a result, it is doing equivalent amount of the work. Therefore, the internal energy of the gas is remaining constant, but at the same time it is undergoing expansion. That means because of absorption of energy, the expansion of the gas is taking place. That means at constant temperature, when the energy is continuously absorbed, expansion of the gas is taking place. Therefore, expansion, if you assume expansion is one particular property, we can say that expansion is naturally taking place. Therefore, during the isothermal expansion, the del G is always negative. Whenever if the del G is negative, that process is always spontaneous. Because of absorption of energy, the gas will definitely undergoes expansion. Hence, del G is equal to negative. Next, if the gas undergoes the gas undergoes expansion, definitely the entropy change will become positive. Entropy change is positive. Next, already we have calculated that enthalpy change is 0. Enthalpy change is 0. Therefore, according to the Gibbs free energy expression, del G is equal to del H minus TdS. Therefore, in the isothermal expansion, this term is 0. Next, del S is positive. Therefore, this is minus TdS. If this is positive, this TdS will remain negative in the expression. Therefore, del G will become negative. Because when del H is equal to 0, del G is becoming equal to TdS. Since TdS is positive, inside the expression it becomes negative. Therefore, del G is equal to negative. Since del G is equal to negative, then we can demonstrate that expansion process is spontaneous. Therefore, it is spontaneous. Next, similarly, free energy change in the isothermal expansion. Similarly, free energy change in free expansion. In the free expansion, see, the gas is neither spending its own energy nor absorbing the energy. Therefore, internal energy of the gas becomes 0. Next, enthalpy of the gas also becomes 0. Energy of the gas will remain constant. Next, according to Gibbs free energy of expression, del H dG is equal to del H minus TdS. Therefore, this is 0. Next, what is the entropy change? So, entropy change here. See, gas is undergoing expansion from container to the into a large volume. So, because of expansion, this is positive. Therefore, when del S is positive, inside the expression it will remain negative. Therefore, if it remains negative, del G will become the negative. Therefore, during the expansion into the vacuum, the entropy factor is increasing, hence del G has become negative. That means in the isothermal expansion as well as the expansion to the free vacuum, enthalpy change is 0. Therefore, the expansion process is not taking place because of enthalpy factor. Therefore, here the driving force is entropy factor. Since the entropy factor is increasing, the increase in entropy is making the del G negative. Hence, this expansion process under isothermal conditions as well as into the vacuum is taking place because of the entropy factor, not because of the enthalpy factor. That means this expansion process cannot be explained by the first law of thermodynamics, because the first law of thermodynamics says that whenever if the enthalpy change is negative, the process is spontaneous. But here enthalpy change is 0. Therefore, based on first law of thermodynamics, we cannot explain the isothermal expansion process as well as the expansion into the vacuum.